Great. Thanks, Chris.
Thank you.
Hello, everyone. I see a lot of familiar names and faces there. Thanks for joining us. I think some of this is going to be pretty familiar to some of you, and others, there might be some new bits in here. So, oh, sorry, skipped a few slides. So if there's any questions, we'll deal with those at the end. Sorry, my video is not working. I had quite a nice backdrop I was going to incorporate with this presentation, but I'll improvise. So I'm honoured to be asked to give this fourth talk on closed-loop boreholes, and this one is about geology and soil. We are going to consider the importance of understanding the geology of the soil, the ground conditions beneath your site, and what implications that has. And I'm going to conclude with an idealized process that you would go through. Every job is different, and so often we're brought in to look at these sort of things late on, but ideally, we'll go through ideally what you would do. So I'm a hydrothermogeologist. I head up the team at BA Hydro Solutions. We do an awful lot of desktop studies into anything, particularly in the ground, whether it's water, the thermogeology, getting water in or out of the ground, heat in or out of the ground. And I've been doing this for about 20 years now. So, so this is the fourth in 3 talks. The other 3 are well worth having a look at, and they're all available through the Ground Source Heat Pump Association website on YouTube. And so today we're going to look at the geology, the hydrogeology, thermogeology, soils, etc. So why do you need to seriously consider the geology in the soil? We're going to have other slides that go into that and the implications of not considering it or not being aware that you might have some issues. We're going to look at who should consider the geology, the soils, how you can do that, and what to do with the information that comes out of it. Unfortunately, we do generate a fair number of reports, and the customers only ask for the report, and I do wonder then what happens with that geological information and how they are able, whether they're actually best able to get the value, the true value out of it. And then when should you consider the geology? And I've got at the end of it a case study for our offices here in Cambridge. So why consider the geology in the soil? So understanding the geology of the soil or the conditions that are present beneath the site, it is a critical part of the process. It forms part of the feasibility study or the risk assessment, or sometimes they're called impact assessments. And those desktop studies have all sorts of different names because they, depending on the nature of the project, whether it's domestic or a commercial project and the scale, they're often written, they're nuanced based on what particular who your audience is, who's going to be reading and what needs to come out of it. But they all really do a fundamental thing. They look at the geology beneath your property, beneath the site, from ground level down to and a bit below the deepest you might consider drilling to, so that you are understanding what's down there and the geological hazards, the lithological properties of the horizons, the thermal properties of those strata, and how they vary, if they're dry or wet, and is the groundwater there, is it moving, where's the water table going to settle, will it be artesian? And all these things then inform the architecture of your project, the design, the cost, how that system might operate, and that, or how it might be developed. Where would you distribute your boreholes across the drill area? How did you have the luxury of being able to move them around? And if you don't, then it informs how you develop the design to account for the issues that are there and you just cannot avoid in the ground. And then into the future, it may affect how you manage and maintain the systems and the schemes to make them a success. The geology, or the information about the soils, is one of 3 critical parts in the design. We feel that you need to take the geology of the soil, the properties of the ground, as important. The weight of it is as important as the plant room and how you're going to heat your building or whatever you're going to do with the heat or with cooling, as much as the load. So if you have a very good plant room scheme and you've got good loads, but you don't understand the geology, then you're probably going to have problems. So if one or more of these three elements aren't dealt with properly, then your scheme could well fail. So who should consider it? Well, it can be considered different ways and by different parties involved. But fundamentally, the person or the company responsible for designing the system must also take responsibility for characterizing the soil or the ground conditions. And they, whether it's a person or a company, needs to take responsibility for the design to be confident. They need to be confident and competent at interpreting the geology. There are other responsibilities within the delivery of a system. The driller has responsibility, and there's communication responsibilities between, if we're involved, or a consultancy like ourselves who are quantifying, characterizing the ground conditions, then obviously there needs to be an agreed route of communication so the information can go backwards and forwards to enable the design to be refined and evolve during the delivery of the project. But if a company designing the ground source heating system or arranging for the boreholes to be drilled doesn't have that capability or the confidence in-house, then they need to outsource that or engage somebody who can work in partnership with them to fully quantify and characterize what's there. And that might be just a desktop study, which is commissioned based on a site plan, postcode, and a bit of information about, well, likely to be drilling to 200 meters or 150. And then a company like ourselves and others who are members of the Ground Source Heat Pump Association can go away, do the research, work out what is there meter by meter below a site, determine the lithological characteristics of those horizons and the thermal properties, and then report that back in a format that can then be used, whether you're using lookup tables or you're modeling, but it gives you the information you need to develop your design. It is important that whoever does this documents what the geology they expect to be there and how they've arrived at that in order to validate the design. Unfortunately, we see too many problem jobs where there isn't an audit trail which documents how somebody has arrived at a thermal value for the ground beneath the site. And then it makes it very difficult to, it's not about apportioning blame, but to understand what's gone wrong and how best to rectify the problem. So it doesn't need to be chapter and verse. It just needs to be some notes that sit on the project file so that if at a later date, and it needs to go to the customer really, so at a later date, if somebody needs to go back and look at what was done and why it was done, it needs to be documented. So how to consider the geology of soil? So there are three types of ground source heating system. I know this is about closed loop boreholes, and I'm going to stray very quickly into horizontal closed loop systems and even quicker into open loop systems. On the right hand side of this is pins just showing where we've done all our thermogeological assessments over the years. There's a fair few there, and most of those start with a desktop study, and then we've got the drilling logs from where the boreholes are drilled to validate what we anticipated in advance. So there are companies like ours have got huge amounts of data that, and unfortunately, a lot of these boreholes don't appear on publicly available archives like GeoIndex. Not many closed-loop boreholes get registered, so this information is held privately. Unfortunately, it'd be really good if it was centrally held so other people could use it. It gives you an idea of coverage there. So vertical. So for these systems, the following summarizes the typical ways of starting to characterize the ground conditions in order that they would normally occur. So initially, it's a postcode check. I've got an example at the end of this talk where we'll see that, but somebody will approach us with a postcode and say, a driller might say, so what might I expect at this location? And we give them the heads up. And if there's no issues, And we've got sort of rough figures, some lookup tables about the number of boreholes they might be looking at, and it all stacks up. The client then organises a thermogeological assessment, a desktop study. That then, as I said previously, that details what's underneath the site, and that might be all you need from a company like ourselves. And the installer then may use heat pump manufacturers' designs tools to work out how many meters a borehole, look up tables, although they're not really ideal, or there's a number of software packages people use. Occasionally there may be trial holes drilled and tested, but we've seen that less frequently. Regularly, we're doing a lot of thermal response testing on boreholes, and they might be on the first, second, or third borehole drilled as part of a bigger project as the drillers are progressing onto the 5th, 6th, 7th hole. We do quite a lot of lab testing, so that's from soil samples or cores that come out of boreholes. Sometimes from drilled cuttings, but not really, they're not that representative. And occasionally we're doing geophysical surveys to help us characterize what's down there. This is a very similar process for horizontal closed loop systems. It's a postcode check. We look at soil maps to work out what's there, to give us a rough idea of the moisture content of the soil, the nature of the soil, and how many watts per meter we might, at an early stage, use to get a provisional design. Occasionally we'll do a desktop study, but to be honest, there isn't enough information out there normally to put together a comprehensive desktop study. So normally it's done with trial pits, or maybe the trenches that have been opened will be sampled as the pipes are being installed, and that can be done with in situ thermal testing of the ground, or we have our own labs here. We do a lot of soil testing that are taken from trial pits or the trenches as they're being done. And sometimes we do thermal response tests on horizontal loops once they've been installed. And again, we can do some remote sensing. We've developed a system with the BGS for remotely measuring thermal properties, the thermal conductivity of the soil to about 1.2 meters using drones, which is quite interesting, but it only really stacks up on big projects. And then open loop, again, postcode check, do a reality check. Is there water there? Could you get it out? Could you get it back in again? If so, it moves to a desktop study and modeling. More often there are trial holes, pump testing, etc. And occasionally there's tracer testing to see if there's interaction between abstraction and injection boreholes. Of these 3 different types, what is really key in this webinar is about doing your homework, understanding what is there, and if you don't have the capability within your organization to do that, reach out to companies, individuals who can help you to understand what's there. So what do you do with that information? Well, it's really important that decisions are made based on the geology and the information that comes out of it. It needs to be site-specific geology, hydrogeology, soil characterizations to develop a design. We still see people who come to us and say, well, we got one of your reports that was done for a house a mile down the road, and we thought it would be the same as what we've got here. But it looks completely different. So it does need to be site-specific. The geology, even across sites, can vary. Stratas dip, stratas thin out, and they change lithologically over sometimes very short distances. The information that comes out should be used to develop models to simulate the ground's response to taking heat out or rejecting heat back into the ground. We can do heat or fluid transport modeling, but only if you know what's down there. The design needs to be refined every time there's new hydrothermogeological data that comes in. So you've done your desktop study, you've developed a design, your drilling contractors have been engaged and they're on site. They or the client or client's agent need to really be reporting back to whoever did your geological assessment to start with to say, it is as we anticipated, or no, this boundary came in a bit shallower or maybe a bit deeper, so that the thermal values that have been assigned to those layers and are weighted based on thickness and depth can be recalculated to arrive at updated thermal values to enable you to reassess how many meters you need in the ground. And that might be on a full array, or it might be on a borehole by borehole basis, as they don't always go into the depth you intended them to go in. You might say 10 holes to 150, but some go to 140, others go to 150. And those sort of variations can be and should be accounted for. So the communication needs to be fluid and it needs to be timely. There's no point telling us 6 weeks after you finish drilling what you went into, because it's a bit too late to validate the design at that point. Sometimes the information that comes out is used to form impact assessments. It depends who the audience is, whether it's a client, the regulator, or who the stakeholders may be. But those sort of impact assessments can only be done if you understand the geology that's down there and how your system's going to interact with it. It's really important to understand the geology before you start talking to or whilst you're talking to your preferred contractor, or before you start going out to look to see who you're going to engage to drill your boreholes or dig your trenches. There could be some nasty horizons down there that some contractors sensibly ought to say, look, I'm just not geared up to deal with that, or I don't currently have the capability. So that information is only fair and it's only right that that information about running sands or artesian conditions is known and shared up front, and you can only get that by doing a hydro or thermogeological assessment. It enables you to be prepared before you get to site. Hopefully it enables you to avoid disasters, but there are certain conditions that, in Huntingdon, for example, there's artesian groundwater within about 40 meters of ground level. If you want to put a sensible closed loop system in there, you can't really avoid it. So you can go prepared if you know what the scale of that artesian issue, where it's going to happen. You can plan and go prepared. And in doing so, you can manage your project, and you've got to make sure you've got the right people present at the right times. So when to consider the geology? Well, I think it's pretty obvious to all of us, as soon as possible. Before any major decisions are made, we have a site where I fear that decisions to push ahead with closed loop were made before they really understood the full cost of it. And now there's a great deal of pressure to try and make a system work within a very small budget. And it's those sort of projects that worry me, that there's going to be a compromise somewhere. And we may not get told what that compromise is, and it might not go in quite as we design it. So you start by assessing what might be there in designing and going through design iterations, and you end up, or you should end up, knowing what is there and how, and that it's been accounted for in the final design. It's really important to collect and interpret the drill cuttings, to review the driller's logs, to measure the ground temperature, and to complete tests and samples and document what's there. So in this slide, we have a picture of one of our thermal response testing rigs. It's measuring a borehole, the thermal properties of the borehole. It isn't cheap to do a thermal response test. We've got 3 rigs. We replace the heating elements and various parts in it on a very regular basis to make sure they're working as close to perfectly as possible. So these are pretty expensive bits of kit. So it's not always possible to do a thermal response test on every project. They're not big enough, or there isn't enough budget. But one of the next best things you can do is, obviously, it doesn't cost you anything, is to collect information on the geology as the drill is going down, and then to take temperature measurements down the closed loops once they're installed and your grout is cured. And that can make a big difference to your design if it gets fed back into the design in time to make those amendments whilst the driller is still on the next holes. So here is a typical process. Postcode check. We then do a preliminary design. If that all stacks up, then it moves forward to a desktop study, or if it's a horizontal system, typically it'd be field testing or maybe lab testing. Then we develop and refine the design to a point where we're on site, or the contractors on site, you drilling or excavating, and measurements are made. The design is reviewed and revised, and we go through a process where there might be a number of design iterations and minor changes. You hope it wouldn't be major whilst the system's being installed, through to the system, the scheme being, or the ground collector side of things being completed. So here's an example. We'll do check the postcode. So SG86PZ, that's our office in Cambridge. We're on chalk. So, well, it's lower chalk. It's actually the West Melbury Marley chalk. And this could have a thermal conductivity of up to 2.5 watts per meter Kelvin. And our offices here, we've got several hundred square meter offices. They're quite well insulated. We need about a 40 kilowatt system. Assuming a COP of 4 and using the lookup tables, which we aren't a fan of, but anyway, that indicates you might need around 790 meters of borehole, which is equivalent to around 5 holes to 158 meters. That's great. Someone might push ahead and install that system. The problem is the geology is actually more complicated, and the chalk's only around 10 meters thick over multiple layers. So this is where we come in. We look at the geology, and actually there's drift as well on top of the chalk, so it's not straight into chalk. The water table is quite shallow. We go through the chalk into the gold, into the green, lower green sand, and then there's a condensed sequence of Kimmeridge clay, Oxford clay, great oolites, Lias clays, etc. And then we get to an unconformity, and then there's carboniferous limestone at about 115 to maybe down to 130 odd. So for those, we can then recalculate the thermal properties for each of the strata and assign a range of thermal properties and calculate what they might be, a range for different drill depths. So as a minimum, this is the output you get from the thermogeological assessment, and you could use that with the lookup tables. So if we went back to lookup tables, that again suggests you might need 1,000 meters of borehole, which is, so it's just gone up. So which one was right? Well, we would advocate doing a design. If you model it using these thermal values, we then arrive at 4 boreholes to 158 meters, so 617 or so meters in total. So that is potentially going to save you, I mean, compared to 1,000 meters, it's a big saving, but compared to 790, it's going to save you at least £5,000 in drilling costs, and it's going to cost you maybe up to £1,000. So this is just an example as to, it's the lookup tables were not intended to design systems. Unfortunately, it probably is the most common way systems are designed, ground collectors for systems are designed. I'm not trying to scare people. I'm just we're trying to point out that there are errors, faults, problems that could arise from this. And you can look at a geology map and think, hey, I'm on chalk. And most of us understand that these beds have got thicknesses, but unfortunately there are systems being designed based on what's at ground level without too much thought about what's below it. That takes me to the end. I think just about on time. I'll hand back to Chris.
Thanks very much indeed, Tim. That was very interesting. We haven't had any questions, one comment, but no questions so far. So if I can just encourage those in the audience to post any questions in the chat that they have, whilst I take a comment really from John Findlay. So we work in the Ground Source Heat Pump Association very closely with the British Geological Survey, the BGS, and John's asked us to remind everybody that we are in close liaison with them to register more closed loop boreholes on their platform. And so if there's anybody out there who does have drill records, whilst it isn't compulsory to do so, we would really encourage our members and anybody else to lodge those records with the BGS. Tim, do you want to say anything on that and how useful those records are?
I think that I entirely agree. We need to encourage our customers to do that more and more. In putting this together, I had a quick look at a local job, and I was pleased to see that just a couple of miles up the road, the records for the closed loop boreholes are on the BGS. So there are more and more going on.
Excellent. So a question's come in from Robin Curtis. Could Tim comment on the use of lab testing versus in situ testing?
Yes, certainly, Robin. So we do some lab testing on cores that come out of trial holes, but very few are there are very few core holes drilled for closed loop. The lab testing really is on undisturbed soil samples. Our preference is really, though, to be getting the samples, testing them in situ on site. We do get a very good correlation. We've got as a lab, and I think all labs approach this in a robust way, or they should be. The controls are in place so that you are getting representative samples and knowing when to reject them and not test them and send them back to the customer if they are undisturbed or they've dried out or they've taken too long to get there. So it's important you've got to have the right, sample it correctly. It needs to be tested in a timely fashion, and only when the samples are appropriate should they be tested. Otherwise, we run the risk of arriving at strange results that may not be noticed, and systems are designed wrongly then.
Excellent. There was a piece of research done many years ago at Oklahoma State University, and they did a multi-site correlation between in situ testing and core sampling, and they found that the core sampling could get about 20% plus or minus over an in situ test. So just thought I'd mention that.
Yes.
Go on, Tim.
No, I agree. So we do a lot of different tests. You know, we got a list of things that we can test on soils as long as your arm. I think these things need to be caveated, and so that people understand what you can or can't do with the results that come out of these tests.
Okay, just a follow-up comment from Robin is his worry is that in situ moisture content, and I guess the corollary of that is variability through the seasons.
It is true, yes. So when we're doing testing, we do try and take into account what time of year we do the tests. If there's enough time, we'll try and leave it so that we go and do the trial pits to try and pick up to make the measurements when the ground conditions, when it's dried out. So we're not basing it on the most favorable conditions. We're getting a representative or maybe worst case measurement.
It's interesting, and a comment come in from John Findlay to say that, and he obviously does an awful lot of in situ tests on horizontal systems, and he's finding that in UK soils he's finding saturation consistently at 1.2 meters. So an interesting comment from John, Tim.
Yes.
Okay, so a quick question from Peter McAvoy. When we're talking about modelling, do you mean something like EED, so that's Earth Energy Designer, or something else like taking vertical thermal complexity into account? I think it's the former, the software packages, Tim.
It is, yeah. So it's typically EED or GLD or software along those lines so you can take the thermal values out and adjust them based. As you go through your design process, you might start with, well, let's aim to do holes to 150, but if through modelling you arrive at 120, then you just rejig your thermal values to represent, so you get a representative value for ground level to 120, or etc.
And just one comment from me on that. We did a comparison exercise between EED, GLD and GLEPRO a few years ago when we were building up the MCS lookup tables, and the correlation, if you get the assumptions the same, is actually very startling. It's incredibly accurate between the three packages. Yes,
they have very similar equations in the background, so yeah, it is reassuring. Some of there was a new version of one of the pieces of software, I'm not going to say, which came out recently, and we had on different PCs, we had an old version, old license, and an updated one, and they were coming out with different numbers on the same software.
Yeah, I've seen that on version upgrades between systems, between the same version of software. I think what I would say is that the current up-to-date packages that I've reviewed are all very self-consistent and consistent with each other. So I think in recent years, things have improved significantly.
Yes.
So just one question which is very pertinent to your talk from Dan. Tim, do you need a hydrogeological report as well as a geo report for a small, so less than 50 kilowatt ground source heat pump system?
So depending on where you get your report from, they will contain different things. If you're doing a closed loop system, then you don't need a hydrogeological assessment, but a thermogeological assessment most of the time will take into account the hydrogeological setting as well. So where there's water, groundwater flow directions, and ours includes geohazards, so that you don't have to have a separate report to cover those things. You can have a hybrid, so if you're looking to do closed loop and maybe have a water well on site, then you can have a hydrothermogeological assessment. Your authors, whoever produces them for you, can often make a hybrid report for you, so that you can. There's not very often the need to have two separate reports looking at different things for the same site.
I think the key point to bring out in what you're saying there, Tim, is even if it's a small system with one borehole, if you've got a serious problem with artesian water, and I'd plug, for those who haven't seen it, John Finlay's talk from last week, then one borehole's enough to get you in trouble. So I think it's a very important point that you assess the hydrogeological risks as part of any system of any size, really.
Yes.
Bean, our illustrious chairman, has asked, if we assume that the market for ground source will increase, and we all cross our fingers, is there any potential for the cost of thermal response testing to come down?
So we've been doing some R&D projects on looking at different ways of doing passive thermal response tests, looking at can we do alternatives. They haven't been particularly successful. The correlation, the accuracy has not been very good. We have hired out our thermal response rigs to contractors in the past, and they've not been run correctly, or one's been blown up. One caught fire in a train station once because it wasn't. So I think it's there is some scope. I think there's some economies of scale. There could be some reduction, but it's quite a lengthy process, and you do need to be replacing the components in it on a regular basis so that you are getting reliable data. What we have done with ours is we've automated them so that we can watch them and control them remotely, so we don't have people sat in fields 24 hours a day for 5 days in a row, and that has helped a bit, but then other costs have gone up. So I don't believe a thermal response test is needed on every project. If you're quite confident about the thermal properties of the ground and the range of potential thermal values is relatively small, then it needs to be a much bigger project before you can start realizing the same benefits for doing the thermal response test. Although one big reason to do a thermal response test is also to measure the efficiency of your boreholes to understand what the true thermal resistance is. But and that's one reason we often discourage customers from doing it on trial holes, because you don't get necessarily representative thermal resistance values from a hole that's been drilled. Drillers haven't got into the swing of drilling it, so it's often good to do the second or third hole, so you are getting a much better impression of the thermal resistance of that borehole, and can work with that contractor to improve it if it's a little bit low, well, poor.
Excellent, Tim. That's really interesting. Just a bit of analysis I did on purely economic terms, and this is about 10 years ago, that if you were to mobilize to site, drill a test bore, test it, demobilize, and go and do your financial close, then remobilize to site. So this is a pure test bore in advance. Up to 10 boreholes, it really wasn't worth it. Above 20 boreholes, it made sense. And between 10 and 20, it was a judgment call.
Yes, I agree.
It's just a rule of thumb I tend to carry around with me.
Yes. So
we have run out of questions in the chat. So if I can just ask, if anybody's got any lingering questions to ask Tim, then I would ask you to type them in now. Well, I just check what the title of next week's webinar is, because I've forgotten. Okay, yeah. So next week's webinar is going to be from Laura Bishop, who hosted one in May, one of our earliest webinars, and that will be on 4th and 5th generation heat networks, talking about the advantages of centralized versus distributed heat pumps and vice versa. So you're very welcome to come along to that webinar next week. Really do hope you're finding these webinars useful, and by all means do email on the screen there, info@gshp.org.uk, with any questions that come to you after we close the webinar. So Robin says, thanks, Tim. Good stuff. Same from me. Thank you very much indeed, Tim.
Thank you. It's a pleasure.
We very much look forward to next week's webinar. And thanks again.
Thank you all. Bye-bye.
Bye-bye.